going for the, already I told in yesterday's class, we have the different method to solve the slope and deflection for various beam. Here we have, we are going to see a basic methods, that is double integration method. The word itself indicating that you have to do 2 times or double time integration while solving using this method. And second one is moment area method. So some of the mathematical terms, it is not possible to solve the finding the slope and deflection in a complex structure. That time you have to get the moment definitely. With that moment area we will get for each member or loads. Using these moment areas, then we will find out the slope and deflection of the each section. Then we will go for a Macaulay's method. See, mostly double integral method and moment area method we will use suitable for a single load, right? Single load or point load. That time this two method is very easy to solve. So we will go for today's lecture as a double integral method. So usually in our syllabus we have most probably a cantilever beam and a simply supported beam, right? And fixed beam. Fixed beam will be like this, right? So this is the load conditions, and you may have a point load or UDL in this location, or UVL you have the location here, or combination you may have the moment also here. Right? These kinds of things we have to find out. And due to this load, what will be the deflection at this point? What is the theta at this point? What is the deflection at this point? What is the theta at this point? You have to find out. You have to find out a common equation due to the loads. Right? First, we will go for the cantilever beam. That is, we have in our aircraft. We have the cantilever beam like this structure. So wing will consider as a cantilever. So engine, you may have the engine here. That point load will carry here, or you have two engine. The wing will have the UDL, right? So we will find a slope and deflection at various end in cantilever beam using double integral method, right? So now we will go for the double integral method. So only using double integral method, we can apply this double integral method for all the types of beams, like point, like simply supported beam, overhanging beam, or fixed beam, right? So for now, in double integral method, we are going to, this is a method. I'll say how to apply this method and how to solve it, right? So here we have cantilever beam, or that is called, we will use it in terms of wings. So we will go for a first case. We will derive that. This is, everything is derivation. We have more than 6 to 7 cases. Today we will see only a possibility maximum using in our aircraft the 3 cases. Remaining you do it your assignment or homework, right? Right? First one is case 1. Cantilever beam which carries a concentrated load at free end. So we have a cantilever beam, the load only at free end, right? So the length of the beam will be L, and we are taking a moment, or we are taking at any cross section x comma x. From the fixed length the distance is x, so total length will be L, so remaining distance will be L minus x. Consider a section x comma x at a point at a distance x from the fixed end. So the theta will be, it is if you want to find out what is the deflection or what is the theta at this B point, this is a B point. Due to this load it will get bend, right? What is the maximum theta? What is the maximum deflection? We need to find out that. So you have to any cross section, any distance. It may be here, it may be here, it may be here, it may be here, at anywhere. So we are taking a x, any location. This is a variable. It may be 1, 2, 3, 4, 5, 6. This is x value. So mx at this point, moment at the mx equal to, we are calculating from the which side? Left side. So we have to use in negative value. That I told. From this, you want to find out the value sign conversion. If you find out from the towards positive means x direction, that is the right is positive. The x positive when the measured from the rightwards. So right direction if you find out means it is in a positive. We are getting in negative value, minus. So that's why I'm putting here minus. This sign convention you have to understand. Right? So W, force into distance. At this point, distance will be L minus X. W into L minus X is a distance. Right? So m we know, we derived m equal to EI d square y by dx square. This you have to remember in all the format. This is momentum you taking at this x point. X equal to force into perpendicular distance. So moment equal to, it is rotation will make sense as clockwise. So we have to use, already I told clockwise means we have to use for a negative. Due to this momentum, I told that if the slope is negative when the rotation is clockwise. So due to this load, this beam will get rotate like this, clockwise. So in another term also you will understand that is using minus. So m equal to EI d square by dx square equal to minus L minus is a momentum we taken. Replacing m equal to EI d square by dx square equal to minus m L minus x we identified. So now we are only applying a double integration method, that is we are going to integrate twice to find the values. So once you twice you will get the deflection, slope. 2 times if you deflect me you will get the differentiate mean, integral mean you will get a deflection. So integration of this value, you do this integration EI d square by dx square equal to integral of minus W L minus X. You know integral no? So if you do this integration, that will term come to dy by dx. So dy by dx is a theta, that is slope. This term will it will affect only x term. So minus W, this term will Lx minus x square divided by 2. This is the integration, you know, right? Plus constant C1. So what is the value of constant? So this is the equation is applicable for this entire beam. Now we have to apply the boundary condition at what location this equation will satisfy. Right? Let us take in a fixed end. Due to this fixed end, it is a fixed. So there will not be any x movement, y movement, theta movement, or slope will not be there. That is a fixed point. That equilibrium is fixed. So definitely in this, you know the equilibrium value. What is the x? What is the y? What is the dy? Right? So in this equation we need the variable. What is the y, dy by dx? What is the variable of x? This is a variable. If you apply these two values, then you will get the constant value. What is c? So x is 0 at fixed point. Dy by dx is 0 at the fixed point. Then you apply here, dy by dx is 0, x equal to 0, then the C1 will become a 0. Then you apply C1 equal to 0, then the final equation of this cantilever beam will be EI dy by dx equal to minus W Lx minus x square by 2 from this equation. So now we identify for the fixed end, not a deflection one. Now you apply for the